All right, hey guys, sorry again about class. I had to keep my son overnight in the hospital just for observation. Everything's good though, so I apologize for that, but didn't get home in time to see you guys. So I'm gonna just kind of finish up section 2.1, what we were talking about, and then start 2.2. I just want to make you aware that my son is running around the house right now as I'm recording this, so you might hear him, or you might see weird pauses in the video. If I have to go keep him from mauling the cat, which is what he's trying to do right now. So, all right, so remember in 2.1 we talked about sets, right? And a set is just a collection of objects. Kind of talked about, a set could be really anything you want it to be. Order doesn't matter in a set. It's just a list, a collection of objects. We talked about the empty set, which has nothing in it. And kind of chatted about how this is a little bit weird, right? But this technically is not the empty set because this has something in it. It's the empty set. Now that's kind of strange. Again, that one you might have to, sit quietly by yourself somewhere, as my professor used to say, and think about that one. So a couple things. Let's talk about some notation before we continue too much further. So some notation, because mathematicians, if anything, are lazy. We just want to make things easier. So, if I wanted to say like 4 is an element of the set, right? A equals X such that X is a perfect square, let's say. Okay, so let's say I wanted, let's not just say that, it is. That's my set A. 4 is an element of the set A, which is X is a perfect square, all elements such that every element is a perfect square. Mathematicians just want to get to the point, right? That's what we want to do. We're not English teachers. We don't want flowery language. I really couldn't care less about adjectives in mathematics. So let's talk about some notation. So some notation we're going to use is we're going to say 4 is an element of. So look at this element, kind of looks like an E. So we use kind of this, or element does start with an E, not just kind of. Leo's trying to unplug my computer. Yep, nope, Leo. Okay, I'm back. That probably didn't look like anything, but Leo was trying to break my computer. So we have, we use this kind of weird E-looking thing to say that 4 is an element of something. So if I had like 4, if I wanted to say like 4 is an element of A, I don't want to write all that out, so we use this little kind of weird E-looking thing. Okay, so it's just notation. So this guy right here, we use it all the time in math. You may have seen a math teacher use it. This means is an element of. So in my example here, literally what I would say here is this is 4 is an element of the set A. Okay, we can also say things like what would I could say like 5 is not an element of A, and that's kind of similar to if we had like a not equal to or something. Leo agrees with me. This is not an element, is not an element of. So you'll get used to seeing this notation. It's super useful notation. Apparently Leo thinks it's so exciting that he wants to take a piece of Tupperware and rub it all over the ground. So that's it. That's good. I hope that you have the same reaction to this notation. So let's look at a couple of examples. Okay, so my question here is true or false for this example. All right, so the first one, let's say that, let's put this, is 6 an element of this set? 2, 4, comma, dot, 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 thank goodness for the dot, 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 98, 100. Okay, let's look at B. We'll consider each of these. 4 is not an element of this set. Okay, we just saw that one, so this one should be easy. Apparently I have not a whole lot of imagination. I made that one up on the fly, and this is the one that was in my notes, so yeah, no. And how about this one is a tricky one. Okay, So let's see what we have here. So let's look at this first one. Okay, so 6 an element of the set 2, 4, 98, 100. Yeah, because this looks like it's a set of all even numbers. So this guy is true. 6 is an element of that set. Let's look at part B. Part B is kind of interesting. It says 4 is not an element of the set of all perfect squares. We know that that must be false because we showed up here that 4 is a perfect square, right? So this statement right here is false. How could I make it true? I would have to have an element of, not an element of, okay? And then this one is really, really tricky. This one actually is false. So this one is tricky because look at what this is saying. It's saying that the set A is an element of the set A, comma, B. That's not true because this is not just saying it's A, it's saying the set that exists that has A in it. I know that's weird. Where would this be true? If I had the set A is an element of, let's say I had this set, which was the set A, and B. Then this would be a true statement because what does, let's say that this is set C or something. What are the elements of set C? It's the set A, the set that consists of the element A. It's the element A and it's B. So these two things right here are different. And remember, this is really just pure logic. And that's what mathematics is really based on. So I hope that kind of makes sense. If you have questions about that, I can try and answer those maybe in class. But this guy is false. How could I have made it true? By putting a not an element of. I know that's kind of weird. It's weird, right? Yeah, I know it's weird. All right, next thing. So that's just some notation. Next thing I want to do is I want to do a quick definition, and we'll do what I want, apparently. So it always gets mad at me when I do that. So definition. Well, we'll do what I want because there's no one here to say no other than Leo, but I don't think he's paying attention to me. Right now he's destroying his room. Oh, no, he came out of his room. We'll see how much time I have here. All right, definition. The set. Okay, we're going to define a set of numbers here. Mathematicians really like to classify numbers and put them in sets. And this set right here is the set, this is called the natural numbers. The set 1, 2, 3, 4, 5, 6, 7, 8, right, and to infinity is what we call the natural numbers. 0 is not included. The reason we call that the natural numbers is it's kind of our counting numbers. So if I started counting the number of people in the room, I would start with 1 and so on and so forth. Most people, I wouldn't say 1, 2, 3.5. Why did I jump to 3.5? Anyway, the set is called the natural numbers, and here is how we are going to denote it. Again, mathematicians are lazy. I don't want to have to write out the actual words, natural numbers, every single time I want to talk about the natural numbers. So here's what we denote it. We denote it as a bold N. So you'll see that, like if you look in your book, it's just a capital N and it's bold, but it's hard to show bold on like the board or on handwriting. So what we do is we do this like double, see, we do these like double lines and then we do an N. Just like the real numbers you've probably seen expressed like that. We use those to indicate that that's a bold R, a bold N when we're looking at handwritten stuff. So we use bolds to classify numbers, okay? Or talk about sets that classify numbers. So for example, let's decide if these are true or false again. Okay, true or false. We should like do a game show or something with set notation. A is the set. Okay, so let's say A is the set of natural numbers. So we'll just use, why did I write that out in my notes? N. Oh, I don't want true or false here. I'm so sorry. I want to, sorry, I'm a little distracted because I'm trying to make sure my son doesn't kill himself while I'm talking or while I'm doing this. So let's describe and using the roster method. That's what I meant to do. I like it when I examples in my notes, and then I don't actually explain what I meant for it to do. So part A is the set of natural numbers less than or equal to 7. Less than or equal to 7. Okay, so how would I write that? So if I think about the natural numbers, what are the natural numbers that are less than or equal to 7? I'm getting ahead of myself here a little bit. Well, 1 is less than or equal to 7, 2, 3. These are just the counting numbers, remember, 5, 6, 7. Whereas the real numbers, I can't really write the number of real numbers less than 7 because there are an infinite number of them, right? There's 1.2, there's 1.3, there's 1.2, 5, 7, 3, 4, 6. But natural numbers I can. That's why we kind of like natural numbers. So what about B? B there, yeah, I know, Leo, is the set let's see, sorry. Whoops. All right, so B is the set of natural numbers greater than or equal to 12. Actually, just greater than 12, let's say that. So greater than 12, so in A, I could actually list every element of that set, but of course for B, I won't be able to do that because the natural numbers are infinite. And I want strictly greater than 12, so I'm going to start with 13. I also could have said B is the set of natural numbers greater than or equal to 13, and those would have been equal sets, okay, because they would have had the same thing. I want to look at one more of these. Whoa, was that a little trippy? I bet it was. So let's look at C here. Let's say, I'm going to call this set D, and I'm going to say that this is all X, such that, again, I want to write this in roster notation. Ooh, look at our new notation with the element, and X is odd. So I want this in roster notation. And let's see what this is set notation. So I want all X such that X is a natural number and X is odd. So if I looked at roster notation here, I believe they consider 1 to be odd. Pretty sure. Just say yes. So look at all of these numbers are natural numbers, right? And they are odd. Yeah, good. Okay, a couple of reminders. Inequality symbols, I know you probably know what these are, but I just want to remind us because I know they can get a little bit weird sometimes. But let's talk about inequality symbols because we're going to use them in some of our set notation. So if I had like X and then I had this little kind of caret thing, I don't know why I'm doing that, sorry. What does that mean? So remember, I know this is silly, but the alligator, right, is going to eat the bigger number. I remember my sister telling me that when I was little, and I was like, that totally makes sense. So which number is bigger? A is bigger, right? And we usually read this left to right. So this says X is less than A, right? That's what that notation means. If I said this with the line, this is X is, again, less than, because as I read it left to right, the pointy end comes first, so that means less than. But this is or equal to, right? Because of the line underneath. I hope you remember this, but just in case you don't, and that's okay if you don't, whoops. Let's just write this down. Let's look at if it looks like this. Okay, then now as I read it left to right, which number is bigger, right? The alligator's eating the X. Do you like my alligator? I kind of do. Alligator's eating the X, so as I read it left to right, X is bigger, so X is greater than, right? Greater than A. Sorry, I messed with my ink phone. I didn't mean to do that. Now it's bothering me. X is greater than or equal to A. Again, as I read left to right, the alligator is eating the X, so that means X is greater than, but it could be equal to A because of that line underneath. And then, of course, we have all sorts of things that we could, you know, if I had something like this, let's read again left to right. X is less than or equal, sorry, A is less than or equal to X, which is less than B. So I could also have, you know, something like this. A is less than X, which is less than or equal to B. So just, that's some reminder of the inequality notations, that sometimes those can be a little tricky if you haven't seen them in a while. Or maybe you've seen them all the time. Maybe you're at a party and you guys are talking about inequality symbols and you're like, darn it, I don't have anything to add to my party. So you should be super happy now that I gave you that. So let's describe using the roster method. Whoa. All right, guys. Let's see. So I'm going to use some inequalities now. So let's say I have all X. Here is the condition on X. So X must be a natural number. Can you hear that pounding of feet? That is my son. Hi, Leo. He's coming to pull my computer. Okay, that had a really weird pause, I bet, when you're watching this. X must be a natural number and X must be less than 200. So how would I describe that set? Natural numbers, so X must be less than 200. So let's think about how small X can be. For a natural number, the smallest natural number is 1, 2, and then I can go all the way up to 200, but I can't equal 200, so I'm just gonna go to 199. Okay, so that's what that notation means. Let's look at another one. All X such that X is a natural number, an element of the natural numbers, right? And let's say, how about this? All right, so look at what this is saying. X is a natural number, and 5 is less than or equal to X, but X must be strictly less than 11. So just look at this. What this is saying is that X must be sandwiched between 5 and 11, right? So if you think here's 5, here's 11 on the number line, X must be in there. X must be greater than 5, but less than 11, right? And then the or equal to here. So I hope that helps you kind of see what we mean. So let's look at how we would do this in roster notation. So what's the smallest X can be? It can be 5, it can be equal to 5, or equal to 6, 7, 8, 9, 10, and do I choose 11? I don't, because it's not or equal to. And that's it. 5, 6, 7, 8, 9, and 10. Okay, I hope that makes sense. It's kind of cool. A couple more things and then we'll be kind of done with this section. Another definition. All right, definition, the cardinal number. So this sounds fancy, and it is, let me tell you. But all this is counting the number of elements in A. So the cardinal number of, not to be confused with the cardinal sin, of a set. Crack myself up. Leo does not think I'm funny. Set A denoted. So here's how we're going to denote this. N, small n of A. Not to confuse that small n with my capital N up here has nothing to do with the natural numbers. This little n in mathematics a lot of time is used to like count the number of things. Maybe I shouldn't say it's not to be confused with natural numbers. The cardinal number is going to be a natural number, so maybe that's why we use it. I don't know. That's denoted. N of A is the number of distinct elements, meaning not the same, right? The number of distinct elements in A, okay? So one quick thing about this is that repeating elements, they don't, in a set, it doesn't add elements to the set, nor does it change its cardinality. So this set right here, 1, 1, 2, 3, would have the same cardinality as 1, 2, 3, and it doesn't change what the set is. This basically what we're saying is that extra 1 right there doesn't actually repeat. Like for example, if I asked you, take the set of all ages in our class. just because I have 3 people that are maybe 18, right? Like I am, just because like 3 of us are 18, that doesn't really change anything. Just because the 3 of us are 18, 18 is still going to be an element of our set, and I don't need to put it 3 times because it doesn't matter. We just want to list the number or all the different ages that we have. So, you know, if you look up here, for example, let's say that this is my set A. Quick example here. What would the cardinality of this set be? N of A, right? What would this be? We'd have 1, 2, 3, 4, 5, 6 distinct, meaning non-repeating elements. So again, that's what cardinality means. So if I wanted the cardinality of the set of all the ages in our class, I would just count all the different ages. I wouldn't count 18 3 times, right? So that's what that means. What's the cardinality here? Well, it's gonna be 1 less than 200, right? So the cardinality of this set, oh, Leo's getting into the dog bowls. He's already spilled the water once in it, so whatever, he can get into it now. You know, for having surgery yesterday, he sure has a lot of energy. Crazy boy. All right, let's look at a couple examples. Find the cardinality of each set. I'm just going to put find the cardinality because I'm getting a little lazy. All right, so part A. What about this guy? What's the cardinality of that guy? Well, it would be 1. There is an element to this set, and the element to that set is the number 0. Actually, if A was this empty set, this guy also is 1, because there is 1 element in this set, and what is that element? It's the empty set. That one's a little bit weird, I know. C, I don't know why I jumped to C. 9, 10, 11, ... 26. So this one kind of gets me sometimes. Sometimes I think it's going to be 26 minus 9. But I'm not sure, so sometimes I just count on my hand. So I have 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, 22, 23, 24, 25, 26. What did I say? Did I say 15? I don't know why I said that. I meant to do 26 minus 9, which is 17, and that's what we got. You should verify that for me, though. Do you ever do that where you like mess up? Like, I get what subtraction is, but is that going to work? What about this? What about the empty set? What is the cardinality of the empty set? Well, let's think about this. I mean, what is, right, the empty set? The empty set is a set that has no elements in it, no matter what. So what's the cardinality? Well, there aren't any elements. The cardinality of that set is 0. That's the only set that has cardinality 0 is the empty set. All right, cool. And now I just have a couple more things and we'll be done. 2 more definitions. Sorry, lots of definitions. So maybe this is good that you can like sit and fast forward through me. Don't you wish you could do that in our class? Like fast forward me? Set A is equivalent. Okay, so let's talk about, this is kind of a little bit weird. Equivalent to set B if A and B have the same cardinality, meaning the same number of elements in the set. That's all that means. So this is kind of interesting because in mathematics, notice equivalent is not always the same as equal, at least in set theory. Equivalent just means we have the same number. So, for example, I have 3 children, right? So if I take, let's let A be my children, okay? Anna, Eliza, and Leo. And then I'm going to let set B be the animals we have. Now, I have some sad news here. Lucy is my dog who I had for 16 years, and I had to put her down this summer, which was one of the hardest things I've ever had to do, but I still consider her an animal, so I'm going to go ahead and put her in my set. So I have, so A is my set of children, B is my set of animals, and we actually say, that A is equivalent to B. I know that's kind of weird, but equivalent, okay, just means that they have the same number of elements. And sometimes, I don't know if your book does this, but we do this. This is A is equivalent to B. They're not equal to each other, but they're equivalent to each other, meaning they just have the same number of elements. Meaning I could find a one-to-one mapping from one element to the other one. Okay, so I hope that kind of makes sense. That's all it means that it's equivalent. Okay. Leo. Oh, sorry. Leo just unplugged my computer. I think we're gonna do nap time here pretty soon. Yeah. Okay. All right. So let's look at some more examples because that's what we should do. Because that's how you learn, is by seeing examples, right? Oh, maybe I don't learn because that always happens to me. So determine if the following sets are equivalent. If the following sets are equivalent. Okay. All right, so let's say that A is X such that X is a vowel. Okay, it's kind of weird. And B such that X is a real or a natural number. I know my child is crying, he's fine. And X is between 4 and 8 and could be equal to 4 or could be equal to 8. All right, so let's look at the roster method. That's how I usually tell. Vowel A, E, I, O, U, right? And what is B in the roster method? You almost have to put it in the roster method to see the cardinality. I mean, unless you can think. I hate that though. But you can think. So let's look at A. How many elements? What is the cardinality of A? The cardinality of A is 5. What is the cardinality of B? Oh, look at that. Oh, what do you know? I gave you an example. So we say that A is equivalent to B, okay? Totally different sets, right? We're not saying that there's any relationship between the elements of the set. That's mathematics doesn't care. Mathematics doesn't care what the sets actually, the elements are. All we care is that they have the same cardinality. Hold on, I'll be right back. Okay, so I hope that makes sense. Last definition, and then you're probably, we're 27 minutes in. I bet you've probably had enough. And then you get to watch one more lecture. I think I'm going to record you another one. All right, definition, set A. When are they equal? Is equal to set B. Now Leo is taking the heating registers off. Whatever if it keeps. Okay, so, oh no, he's got my sunglasses. Hold on, I'll be back. Okay, if A and B, so they are equal to each other, if A and B contain exactly the same elements. Sorry, I'm kind of squishing this. Regardless, not irregardless, guys, that doesn't make sense. Regardless of order or possible repetition of elements. Repetition? I don't know, whatever. Again, I'm a math teacher, right? I don't need to spell good. Wow, sorry to squish that. So regardless of, I want to kind of keep that definition up, so I'm going to just work up here. Regardless of repetition, or order of elements. So the thing here is, I want to put a little, in your notes, put a little note under that. Two sets, two equal sets. Two equal sets are also equivalent. Because equivalent just means they have the same number of elements, okay? So equal implies equivalent, Equivalent, however, does not always imply equal. So like the one we just did where I had the set of vowels and the set of numbers, those are equivalent sets, but they're clearly not equal because the elements aren't the same. So for example, let's say that we have A is equal to W, W, C, C. And let's say that B is equal to W, C. Let's look at the cardinality here. Cardinality of A is 2. Remember, repetition doesn't matter. Cardinality of B is 2. What are the elements of A? W and C. What are the elements of B? W and C. So we say that A is equal to B. Now that's weird, but remember, we only just care about what the elements are. Just like if I listed all of the ages in our class, I don't care that I'm 18 and someone else is 18, and another person's 18. All I care about is that there are 18-year-olds, okay? So I hope that kind of makes sense about what that means. A really quick example, another quick example. What if A was 4, 5, and the empty set, and B was 4 and 5. Are these equal? Not equal, right? Because B does not have the empty set as an element of it, and A does. Also, look at here, the cardinality of A, right, is 3. What's the cardinality of B? It's only 2. Okay, so not equal. Maybe they're friends, but they're not equal. Actually, what we're going to see is that B is a subset of A. We're going to see that in the next lecture. Oh, Leo's running around cleaning in quotation marks with a rag. Good job, buddy. All right, you guys, I hope that makes sense. If you have questions, I should be on campus on Wednesday, office hours 1 to 3. Come by and see me. And then, of course, we will kind of finish. Well, we won't do too much with this actually on Thursday because we got to move on. But hopefully this will help with the homework, and I'll put up the solutions to the fun sheet. All right, that was fun.